So tell me if you cannot hear me. So we're gonna still doing our discussions more on the Lejang transform and deeper properties of like the interplay between the Lejang transform, the Lagrangian and the Hamiltonian. And as I promised, we're gonna go a bit deeper than advanced, chapter 3 of PDE. And it's not a problem if you haven't studied this before because we start from the beginning. We're gonna do also some interactive discussion today about like the subdifferential set, subgradient set. We're gonna discuss about that. But I mean, the plan of the lecture is that I'm gonna review quickly, the Legendre transform, and then we're gonna prove the second result, saying that if we take the Legendre transform twice, we get back to the original convex function. That's the first one I'm gonna prove. The second one I'm gonna prove is that no, not prove. The second one, which is extremely important, is that we're gonna discuss when do we have equality in this sort of duality, and this is a substantial viewpoint from going between Lagrangian viewpoint and Hamiltonian dynamics. We're gonna use this many times throughout the class, and surely I'll remind you. Um, and then after that, we're gonna discuss about one first simple thing yet quite interesting, is that if you have a convex function which is just differentiable, then you automatically have that function is C1. So it start getting interesting. But don't worry, as I said, we're gonna start from the beginning. Okay, so I hope that's clear. And then after all, we're gonna do an interactive discussion about the subgradient, and I also have a question for you. By the way, I mean, all the question I've posed for you, eventually it's gonna be composed together to make a problem sets, and that's it. You write out your problems and turn in. That's all. I mean, because that's the goal of our class. You get things for further study or further uses or further research or something like that. Okay, so let's start. So let me first remind you very quickly about the transform. All right. So I mean, we have defined it. So again, the definition, let me rewrite it here, although we have defined it already, but let me rewrite it here and I redraw just a quick picture for you. For any given vector v, you would have LV is defined to be the supremum of all P in Rn of P dot with V dot product subtract H of P. And this one can be defined for general Hilbert spaces, or for in general structures. We are just doing it in Rn. And in terms of picture, last time we talked about that. Let me record here. So if you draw the graph of H, assuming that this is H, then what you're doing is that you're taking the difference between, in 1D, P dot V is this line, right? Going through the origin. And you're taking the difference between P dot V subtracting H. In this case, clearly P dot V is below the graph of H, so that the Lagrangian at V is negative, right? And what you can see that is either you are taking the supremum, the maximum value, or the other way, the geometric picture you can do is that you are lifting the plane or the line up until it touches the graph at this point. And and that gives you that this line having the equation for this line is P dot V plus C, little c for some C, for example. And this little c is just the C on the graph, this point, the value here. And then you can see that in this case, you have LV is going to be exactly minus C, right? That was the geometric interpretation we did last time, okay? And there are various ways to view that, and that's good. Again, interrupt me or ask questions, whatever you feel fit. And the first lemma we did last time, I record here, is that under the Legendre transform, we have the finite and convex and superlinear properties all together. I mean, the three things together are preserved under the Legendre transform, right? You start with a function which is finite, convex, and superlinear. Then under the Legendre transform is also finite, convex, and superlinear. Okay, so those were the things we discussed last time. So today let's move on, and we're gonna prove an important result, as I mentioned. That is, if you take the Legendre transform twice, you get back to your original convex functions. And by the way, for this result to hold true, I don't need superlinearity. Convexity is enough. So if you take a convex function, you do Legendre transform twice, you always end back with your original one. Superlinearity is, for our purposes, to have things finite and nice. Okay. So to prove this result, and I record here, L star P is that you are just taking the Legendre transform of L. So you do supremum over V of V dot P minus L of V. Okay. So to prove the results, we prove in two steps, So basically we want, in order to prove L star equals to H, we're gonna prove, that L star is less than equals to H, which is step number one. And then step number two is that L star is greater equals to H, And typically in this kind of proof, when you do, two-sided inequality test, then one of them is often the case simpler than the other. I mean, not really always, but that's that. So how do we see things? You see the key thing is that the duality is happening all the times, is that you always take like P dot V minus H of P, or you take P dot V minus L star of V, right? So you see that the dot product P dot V occurs many times, which is exactly the plane or the hyperplane or whatever. So clearly, from the definitions, one clear thing, one clear message for us to take out is that, from the definition that I just connected to, you always have that L V is always greater than equals to P dot V plus H of P. And this is giving us the very important inequality. This is often called the duality inequality, or inequality coming from Legendre transform and stuff like that, which is you take H of P plus L of V. This is greater than P dot V. Okay, as simple as it looks, is one of the most important inequality, in this whole field. And because of this, you can switch back and forth, right? From this inequality, you can, move LV to the other side. You have H of P is greater than equals to P dot V minus L of V. And because this is correct for all V, you can take supremum over V. If you take supremum over V, you have this first-sided inequality, right? So that's rather simple. So the key thing is that if you take H of P plus L of V is always greater than equals to the supporting hyperplane. Basically, that's what it means. Okay. So we are done with the first one. Okay? So that first step is done. Now the second step, this is a little bit trickier. It's a little bit trickier because of the fact that, maybe I can sort of, it's a little bit trickier because of the fact that, we have to make choices. And sometimes the choices are not natural, but, we can take times to get used to that, right? Because you have just write out the first definitions, which is L star of P is supremum over OV of P dot V minus L of V. And then I can also write out the definition of L of V, right? So definition of L of V is, of course, P already occurs. So I have to change the variable, the parameter to R. So this is the supremum of OR in Rn of R dot V minus H of R. Okay. And then I have minus of sup here. I have the minus size here. So if I move the minus size inside, then the sup becoming the inf, right? So sup becoming inf. So I have L star P supremum over V, infimum over R. And because I unpacked all the brackets, I have P dot V minus R dot V, that becomes P minus R dot V plus H of R. Okay. So that's that. I mean, up to now, nothing is tricky. We are just trying to play, write out the definitions as usual in mathematics, right? So let me write out that formula again. So I have supremum of V, infimum of R, of P minus R dot V plus H of R. Okay. So far, to me, at least up to now, there's nothing tricky. Now, the next step is tricky. I mean, how do I get about? I mean, because I write out the second step, this is what we need to prove, right? How do we go from here to the fact that we show, I mean, our goal is to show that this is greater than H of P. I mean, at least, again, as I said, Legendre transform is not natural from the first hand. It's a beautiful transform, but sometimes it's mysterious. I mean, so it's not very clear to me of how to go from this sub-inf greater than equals to H of P, right? But now, I mean, now there's a thing about convex function, right? Assuming that everything is nice for now, no corners. Last time we talked about corners. So one clear thing that I needed to assume here is the fact that we need to assume H is in C1, okay? Again, this is absolutely not natural because H can well have corners, but for now, let's assume everything is smooth so that we can talk about derivatives. As you see, there are two terms occurring here. I have H, oops. There are two terms I have here. I have H of R. I need to compare that with H of P, right? So, and you can see that H of R is this value, H of P is this value on the graph, okay? And you see that naturally I can use the convex property, right? The convex property tells me that I have H of R is greater than equals to what? H of P plus dP dH, the gradient at P, dH of P multiplied with R minus P. That's a natural property, right? If you use the the affine function touching the graph at that point, and it's always below our graph, right? That's a convexity property. And if you compare, right, this is exactly H of R occurring, H of P occurring. So naturally you see that these two should match. Okay. And that's why in the proof we chose naturally V is dH of P, and we are done, right? Because of what? Because we are taking supremum over V. That means that it's the best case scenario for all the V's. So if I choose one V, that's fine, right? I choose the one that suits for my purposes. That's fine. And then we are done, right? Because if I choose V is exactly dH of P, what I wrote down here is exactly just the inequality here. I mean, what I wrote here, whatever, whatever looking complicated here is exactly here, right? So we are done. So with this specific choice of V is dH of P, then we have that, hold on, did I say something? No, yeah, that's correct. Then because of this specific choice of a V, I only choose one V, so L star P should be greater than infimum of this choice of V, which is, this is the choice of V we made. And this one itself, the thing inside the bracket is always greater than H of P. Okay, so we are done. So again, as I said, I wouldn't say that this transform is natural. And the second step is harder than the first step, because the first step we only needed to use the very natural duality inequality. The second step involves the choice we need to make for V, right? Because it's supremum over all V. However, if we do the backward sort of like deduction, then we can guess what's the point, right? Okay. As I said, I mean, I'm getting used to this kind of duality. I, I told you I have been wondering why there's only one, right? It's interesting. Um, okay. So we're gonna come to this point of discussion. Let me just raise it up first, and then I'll leave it for now. We do the important stuffs, and then we get back to this. This one is actually important. That in the above proof, we did use the point that if we were to have, uh, we need H in C1 so that we can have DHP exist, because it was the case that we chose V equals to dH of P in the proof, right? So that's seemingly an important point that we got to address, right? Now, what if we don't have HC1, right? Many times we have seen, and last time we already discussed that H might well have corners like that, right? So H might not be differentiable. If this is 1D picture. In multi-D, I mean, the graphs of H and the corners, the points of non-differentiability can be very complicated. So if it's not differentiable, then what should we do? Um, of course, if you have done some study about convex function, it's a natural object, and it's a natural question to ask. And it's clearly that at the points here that the function is not differentiable, although you cannot define derivatives, but you can always have supporting hyperplanes below the graph, right? In fact, you can find in 1D pictures, you can find many lines of touching, many affine functions that touching the graph at those non-differentiability points, right? And that leads us to the definition of so-called subgradient. So this is del of HP, or D minus of HP, is the definition of subgradient of P. And we say that a vector V is in the subgradient set if exactly that the affine functions is below H and it touches the graph at P, right? So this is called supporting hyperplane. So this is an affine function, if you wish, or a supporting hyperplane. Okay, and those one touches H from below at P. So it's below the graph, but it does touch the graph at the point P. Okay. So this is a very important claim, that if H is convex, then although it might not be differentiable at some points, but the subgradient set at any point is non-empty. In fact, you can prove that this set is convex. The set is convex is easy, because if there are two affine functions below, then any convex combination of those is going to be below. That's clear. So convexity of the subgradient set is easy. So I would say that del HP is a convex set. So this is easy to see. but then how do we prove this set is non-empty, right? And this is clearly false for general functions, right? There, you know, we all know the function like sine of 1 over x that is oscillating like crazy near 0, right? Or maybe x times sine of 1 over x or something like that. It's oscillating like crazy near 0. It's not differentiable at that point. And also you cannot find any sort of supporting hyperplane or something like that. Yeah. Okay. But for convex functions, when it's sort of like convex shapes, like the bowl up, then you can always prove that the subgradient set is non-empty. So I'll leave this one for discussion later. And I would like to hear your inputs of how do we do this question. This is interesting. Um, I have never actually read this proof in Rockefeller books. Rockefeller's convex analysis is like a Bible for convex analysis. Um, I have some proofs in my mind. We can talk about that. I want to hear your inputs, and maybe you can tell me if you have seen this. The what's the proof in Rockefeller book? Okay. All right. Tell me if you have any questions or concern. All right. Then the second point I want to discuss today is this extremely important inequality. I cannot stress enough how important it is. I mean, it's sort of like maybe the second most important inequality to me after Cauchy-Schwarz inequality. Okay, Cauchy-Schwarz, I don't know. It just I don't know how to put it, but maybe it's gonna occur in our lecture, in every lectures in our class. Maybe, I don't know. Maybe I'm wrong, but anyway, it's a very important inequality. And the question is always, when do we have equality? Okay, so equality when? Okay, and as I said, this is an important question to address because it's relates to it's really related to what we're gonna discuss later about the duality viewpoint between Hamiltonian mechanics and Lagrangian, like minimizing problems, or Euler-Lagrange equations. And well, if you look back, there was a problem okay, I can write here, although it's written down, but I mean, maybe you can see it clearer when I write down. I have this maximizing or minimizing problem. H of P is supremum over Q. Okay, yes, I remember. For some reason I changed this one to Q. Q dot P minus L of Q. And this supremum happens at V, right? And clearly we have taught our student in multivariable calculus, right? If we do maximizing, minimizing problems, if everything is nice, then the maximum, this one is when, so max happens when Q equals to V, right? And at the point of maximality, then clearly the gradient of these functions inside here, the gradient of this function got to be 0, right? And if everything is nice, then you should have that the gradient of these functions, Q dot P minus L of Q, at Q equals to V got to be 0, right? And the gradient of this function in Q, this one is exactly P minus dl. Q equals to V is 0. So that means that you do have that P is dl of V. right? So it happens if and only if P equals to the gradient of V, right? But if your function is not differentiable, then you can replace it by saying that P is in the subgradient of V, of L at V. Okay, and this is exactly what I meant. And similarly, again, it's really important that not just that you have one-sided inequality, right? Because if equality happens, it happens for both. It happened for 8 equals to sub of something and is equal to L equals to sub of something. So this is sort of like when equality happens, it happens for both, for the dual formula for H and the dual formula for L. So you see that it happens not just here, but also here. So what is important here is that both happen together. This is amazing. I mean, not just one, but both. So keep this one in your mind. And I put a box here. So this, oops. So this happens if and only P is in the subgradient of L, if and only V is in the subgradient of P. And later on, we mostly gonna deal with smooth enough functions, in which case, then uh, so if things are smooth, then equality if and only if P equals to dL of V, if and only if V equals to dH of P, and this is exactly the bracket of relations that I wrote down here. You're gonna have HP plus L of dHP equals to dHP dot P, and this one. Okay. Again, I cannot stress enough how important they are. I'll come back to this, when we reach the connections between Hamiltonian dynamics and Euler-Lagrange equations. You're going to see one implies the other and vice versa. Okay. Any questions or concerns? Okay.
I had a quick question. So, can you say a little more? So you said that if it's differentiable, there's only one of these points. Why is that true?
Sorry, what can you repeat
So
your
yeah,
question?
if L is differentiable, then there's only one of these subgradients.
Yes. Okay. Sure. That's a very good question. Can we keep it also for after what I proved? So the question is that you have the subdifferential set is a convex set, non-empty. I mean, we have to prove that, right? And then we also need to prove that if it's differentiable, then the subgradient set has only one element, which is exactly the gradient. Okay. So thanks. That's a very good question. We're gonna come back to that as well. Okay? All right. So let's prove this result, and then I really want to go there. Okay. Well, the proof this result is not so hard. I mean, right? We have it's convex, it's differentiable. We need to prove it's C1, meaning that, I mean, we are just gonna quote the definition, nothing more than that, right? We're gonna just prove that if I have a sequence PK in Rn, so that PK converges to P, then we need to show that the gradient of dH as PK converges to the gradient at dH at P. Okay, I mean, just a typical definition of continuity of the derivative. I'm not using anything magical here. And the first thing to prove is that if you are dealing with a bounded set, then the set of gradients of this bounded set is bounded, and oops. Okay, so you take a ball and you prove that dH of a ball is bounded, and again, uh, this is not true for general functions. The gradient can blow up and stuff like that, but for convex functions, you can always use this. Oops, again. I'm sorry. Well, the good thing is that I have the undo button. uh, so you can always have this inequality, and you know that to measure the length of the gradient, you just need to measure the maximum over all vector q less than or equals to 1 of dhp dot q, right? And this is less than difference, so you can easily have that uh, the length of the gradient is bounded by twice the max value of something. Again, this might not be sharp, but you're just proving that it's bounded. Why? Because in order to prove conversion, right? I mean, again, we are in Rn. To prove conversion, we need first to show that this is a bounded sequence. Again, just a classical trick for sequences in Rn. Not a big deal. Okay. Um, the second thing, as I said, we have to prove that DHPK, oops, again, uh, you think of one thing and, in your mind, and your hands are doing different things when you're writing. This is why we have so many typos and misunderstanding when we write papers, because, we think differently. Okay. So we need to prove this, and in fact, you don't have to prove this is true for the whole sequence. You can just need to show that we already show that this is bounded, because PK is bounded, right? PK converges, so it's bounded. You have, by passing to a subsequences, do you have the H of PK converging to V? You just need to show that V is indeed the H of P, right? And that's enough, because otherwise you can just do a proof by contradictions, assuming that this one is not convergent, right? And then you can find a subsequence that converge to a different value, and from that subsequence you can find another subsequence, and by this thing, there's a contradiction anyway. And here we are using stability or continuity, and this is very simple and very powerful, right? I need to show. Oh, now I understand. Sometimes if I'm not writing long enough, it's automatically switching between the buttons. So sometimes I don't know. Um, okay. So I need to show this, and to do this, I just need to use exactly the continuity. So this is basically continuity, and if you wish, this is some sort of stability. We can also use a lot stability of continuous functions in some forms in our class. I'll mention to you how and when. I'm just using the fact that, you know, convex functions, we are using that at the point pkj, we have this relation, right? We use a supporting hyperplane at pkj, we have that relation. And now everything is stable. You let j goes to infinity, h of pj converging to h of p, dh of pkj converging to p, and c minus pkj converging to c minus p. So you have h of c is greater than or equals to h of p plus v dot c minus p. Then you conclude that v is exactly 1 point, which is in the subgradient set, which is exactly 1 point. And that is exactly the question uh, that you asked me earlier, right? You asked me, if it's differentiable, then how do we know that the subgradient set is only 1 point? Okay. Okay, and this remark is natural. Everything holds if you replace the derivatives by values in the subdifferential. So if you take vk in the subdifferential set, if you have pk converging to p, vk converging to v, then v is also in the subdifferential set. So it's a stability result. It's extremely important, and show that for convex function things are stable. And this is a huge subject in optimization. This something sometimes people call this one Clark derivatives, and there are people like Rockefeller, Mokdukovic, and others. They came up with all kind of uh, generalized differentials, and what you need to have is certain stability when you take things to the limit, like what I highlighted here. Okay. So let's come to our discussions. There are now two questions. So question number one, this is quicker. So let me address this one. So and then I'll do interactive discussion with you guys about the other. Um, First one is that if h is differentiable at P, then we only have that the subdifferential set is a singleton, right? Um, okay, first a picture proof. Assuming that at the point P you have two values in the subdifferential set, right? Maybe v1, v2. Okay. Then your function is gonna look like something like that, and it has a corner, right? So it doesn't look differentiable, right? So that's a way. The other way you can think about that is that you can write down exactly the definition, right? You have h of r is greater than equals to h of p plus v1 dot with r minus p. Uh, right? And then let me see what's the best way to explain. Okay, hold on. Maybe the easier way to write is, let me write that like that.
So h needs to be a convex function too.
Yeah. We are dealing with convex function here.
Okay.
Right. Thanks. If it's not a convex functions, then we don't have the definition of subdifferential. Subdifferential is that we are touching, it's the graph is always above the supporting hyperplanes. Okay. Um, uh, Later on, we're gonna talk about different notions, which are gonna be the subgradient and supergradient. That's a bit different, but anyway. So let me do it a little bit quicker here because I want to use time for us in our discussions. So let me write this way so you see that it's easier. R minus P plus omega R minus P. Okay. So this is just a definition of differentiable functions, right? And so if you have V that is not equals to dH of P, and V is in the subgradient set of H, then you also have that H of R is greater than equals to H of P plus V dot with R minus P. You can have that too. Okay. So you clearly see what's going on here, right? We are gonna compare the two relations. Then that's this one gonna give you that you have you can subtract H of P out, dH of P times R minus P plus R minus P times the modulus of continuity here is greater than equals to V dot with R minus P. Okay. And then you combine the two, you have dH of P minus V dot with R minus P plus R minus P omega of R minus P is greater equals to 0. And do you see now that you can come up with a contradiction here? Can some of you tell me? Again, I don't want to put you on the spot, but if you have some ideas here. Okay, maybe let me rewrite this one. I have that this is a fixed vector, which is not 0, right? So you can write like a vector I dot with R minus P is gonna be greater than equals to r minus p omega r minus p, right? A is a fixed non-zero vector, right? So the left-hand side has linear growth. The right-hand side vanishes as r goes to p. Vanishes quicker than linear growth. So you can just simply choose r minus p to be s times minus the vector a or something like that, right? S times minus a. Okay. And you take s greater than 0, s goes to 0 plus, you see the contradiction, right? Because the left hand side is going to be minus s times a square. This is a fixed number. It's going to be greater than minus s times a times omega minus si or something like that. Okay. And that's a contradiction. Does that make sense?
What is the function omega here? That's
omega is just a modulus of continuity, right? I'm using the fact that h is a differentiable functions here. So, you know, I can write out, you know, like the definitions of a functions, that is, if it's differentiable, then you can think of it as a Taylor expansion around the point P, right? So I have h of the zero order terms, the first order terms, and an error term. So omega here is limit of z goes to 0 of omega z is going to be 0. Okay. Okay. Yeah, maybe here I can write down so that you can see, if I divide both sides by s times a, I'm going to have minus a is greater than equals to omega minus si, and as s goes to 0 plus, this one goes to 0, which is a contradiction if you wish.
I see. Thank you.
Okay, cool. Again, there are lots of magic properties of convex function, you know. So, okay, let's start our discussion. I'm sorry, I'm always a bit late for the game. I want to give us more time. But so the question, can some of you tell me, you know, any strategy of how do we prove that the subgradient set is non-empty? There should be more than one ways to think about that. So can some of you have, if you have some ideas, can you tell me how?
One way I've been thinking like is for convex function h, we can do a convolution to get a smooth function epsilon. So then the gradient of the h epsilon we vanishes is gonna select one subgradient.
Okay. Yeah. So that's a good and natural way. I also thought about that a lot actually, and that's, you know, it's so this is the first way. Let me write quickly and then we can. So you take eta as a standard modifier. So this is like baby routine, right? You take a standard modifier for epsilon greater than 0. You define eta epsilon is 1 over epsilon to the n, eta epsilon of x over epsilon. And then you define h of epsilon p is eta epsilon convoluted with h, right? At p. Whatever. Something like that. Okay. So what CERN said is that you have then h epsilon is convex, smooth, right? And you can select like p epsilon is no v epsilon. is the gradient of dh epsilon at p, and you let epsilon go to 0. Okay, that sounds correct and perfect. Again, you got to come up with a proof, you write it down. But I mean, in my mind, for example, if you take a functions like this, if you do convolutions, you're going to have something smooth coming up like that. Okay, so at this point, for example, if you do it like that, then at this point, the gradient v epsilon is always 0. When you pass to the limit, then 0 is in the subgradient at that point 0. Does that make sense? Okay. Any other ideas?
I was thinking maybe you could do like a contradiction where, say for every slope of the hyperplane, if there's a point of where h is below it, then this is going to contradict that inequality we talked about at the beginning of class. Your second favorite inequality, that one.
Okay. Yeah. So yeah, definitely. I mean, to me, I also think about it like that. So the second way is to do proof by contradiction. Right? Because because you can assuming that there's no way to touch the function there, and from there you can you can go about to do in various different ways actually. One way is exactly to use that inequality. The other way is also to use the fact that like you have, this is also an exercise in baby routine, that if you have H is convex, then you have that H is Lipschitz locally, something like that. And if you use sort of like the so-called Rademacher theorem, again, Rademacher theorem, then you have H is differentiable almost everywhere. Again, this is also, I wouldn't say it's a big gun, but I mean, you're using a Rademacher theorem. Then I mean, the proof by contradiction, again, as I said, there are many ways to do this, but one way I was thinking about that, exactly in the light of what you have been talking about, is that although you have H is not differentiable at P, so it's not differentiable here, but you have H is differential here at PK. And I can write out what is dH of PK, which is VK, and then I can use the stability results passing the limit or something like that. So and I I was also thinking about the other way to do proof by contradictions. I forgot, so I no, I wouldn't say out loud because I might be wrong. Other ideas? Or if you have seen other proofs, can you tell me? Because again, I want to see. Convexity is something very mysterious and very rich. There are things that.
I just had a clarification about the first way. So in the first way, we're saying that each of these H epsilons have a subgradient, and somehow when I take a limit, the subgradients converge to a subgradient for the function. Is that how it's going?
Yes.
I see. Okay.
Yeah. Or you can even take subsequences and everything. I mean, like, for example, I was giving you, this is an example. Again, I thought about this, that you have an example. This example I drew is H of P is P. If you do convolution, you think about it. I mean, at the point far away, the convolution is still absolute value of P. But as you get nearer to the corner, convolution is going to make things rounder near the corner. And this is exactly the picture that I drew here. Oops, again. At this point, it's going to make things round, and then the dH epsilon is 0, 0. So if you select V epsilon to be dH epsilon is 0 and you let epsilon go to 0, you only select one point in the subgradient, which is 0, right? But there are other ways you can also use that. You can take P epsilon converging to P and take DH epsilon of P epsilon. You take all possible subsequential limits. And I think, again, I'm not, I think I did this earlier a long time ago, so I'm not very sure, but I think if you do it this way, you take all possible subsequential limit, you would be able to sort of form the whole subgradient set. Although I got to be careful. Yeah, but I mean, this is just saying, right? You know, for example, you have to prove that H of epsilon is convex. It's a fun exercise for you, and everything. And the second way is also that you got to prove that things are there, or I would also ask you if you can use the duality inequality in a in a quantitative way, like what your friend just said. Basically you do prove a contradictions and you try to do it in a quantitative way, then I bet that you can get the subgradient. Okay. Any other concern?
Another thing that you mentioned about convexity, I think if our functional analysis, when we have convexity, we can try to do Hyperplane theorem to kind of find in the hyperplane with hyperslope.
Sure. Yes. So that is a very abstract way. So the Hyperplane is essentially an abstract way to sort of do like splitting, basically, and this proof is going to work also. I mean, the good thing is that it works for general spaces. The not good thing is that it's not constructive. But if you need to prove existence, then that's also might be a good way to think about. Okay. Yeah. So great. I think that we can finish now. So let me just ask the last question. Is the speed okay for you? Is it too slow? Is it too quick? Or is it fine? Okay, good. Yeah, again, our goal is that we get something. You guys get some new stuff. I get something. That's that for purposes later, for research and for everything. Okay, great.
Would you be able to post your notes from during class, the extra notes you wrote on the lecture?
Yeah.
Do you post those on Piazza or on Canvas or?
Yeah, so on Canvas, I mean, what I do is that if you look at the lectures, I post the lecture every day, and then in the reply or comment section, I'm gonna post the post lecture notes. So I did that.
Oh, I
for
see.
The lecture.
I see. Okay, thank you.
Yeah, so I'll post this one right away. Okay, so thanks a lot, guys, and I see you on Friday.
Oh, also we also have Piazza for this one. You just set it up.
Oh yeah, we have Piazza. So if you want to ask Piazza, it's great. Okay, thank you. See you all. Bye bye.